I already said at the end of my last year lecture that the object which we studying is Liouville manifold with convex end, with kind of cylindrical end. So you have a symplectic manifold with a, say, chosen primitive of symplectic form. And there is a condition on this manifold that there exists some domain inside this X such that boundary of this domain is transverse to the Liouville field. I forgot to say, each time when you have such Liouville form, you can also form corresponding Liouville vector field dual to this form. So just kind of like they always come in pairs. And you require that there exists domain such that boundary transfers to this Liouville vector field, and such that everything, so if you take a x minus boundary, that this is just union, this trajectory, it's just you take a flow, it's a union of z to the t of dw when t from 0 to infinity, right? So just everything is just cylindrical end filled by this trajectory. So this is kind of Liouville manifold with cylindrical M, and there is a such manifold have a attractor and or core, so like called core of say x lambda. This is just you take a like intersection of z minus t of w for all t greater than 0, right? So take kind of like this thing and flow with negative flow, kind of like, and you get intersection, you get core. And the like point of no, doesn't matter, not boundary. You take the whole w, kind of intersect. If you take a boundary, you get empty. Yes, right. So it's not boundary. So now what we want. So there is some core, there's some kind of compact subset inside, and in fact, really we're interested. Like we will be thinking about this Liouville manifold just a germ along the corner. So if you have a germ around the core, then
I'm confused. So is this Liouville vector field existing only near?
No, Liouville vector field is given. You have a globally defined lambda. You have a globally defined z, and they, yeah. But now I'm saying like all information. Interesting information just in the neighborhood of core, because everything else you can always reconstruct by adding this field. Of course, you can ask some kind of like qualitative question, but like if you're not interested in anything which like numerical kind of invariance, then this is a whatever. So now we have a very special case of this, and very special case of this is so-called Weinstein manifold. Okay, now what Weinstein manifold is a kind of subject to certain uncertainty. That means that there are kind of like several definitions I will give you, we can choose, but it's not clear what is the most satisfactory definition. So, okay, so what you would like to say? You would like to say, so let me kind of discuss different versions and then kind of how they're related. So first you say, okay, so there exists this vector field admit Lyapunov function. That's kind of more traditional property that we, in addition, require that Z admit Lyapunov function. That means that there exists some function such that on our manifold such that vector field so it's gradient like for this. So what it means? It means that df of z is greater or equal than some positive. It could be maybe not necessarily function. Or we say, because I'm actually interested everything just near the core, so I can think it's compact. Then it greater or equal than c, and times kind of norm z square plus norm df square. This is how usually define gradient-like condition or Lyapunov condition. And of course, away from critical point, it just means that it's transverse to the level set, and at critical point, it's certain constraint. And this certain constraint is kind of like precisely what makes it very unpleasant. Because this is, okay, good definition, but now for all, but in principle, this does not prohibit our vector field to be extremely, or zero vector field be very degenerate. And sometimes we would like to perturb this thing to make it non-degenerate, and that's completely unknown. That's an open problem. We don't know. Can Liouville vector field be perturbed, keeping it Liouville vector field? Keeping it Liouville vector field in such a way that, for instance, function f become Morse or kind of become generic. We don't know that. So that's make this definition unpleasant. So there is a kind of another proposal. Yes?
In the background, are you fixing an almost complex structure?
No, there is no almost complex structure.
How do you get the norm?
Yeah, because this condition independent on the choice. You can pick any background metric you want. And this condition is dependent. You get different constant, but it's the same. Doesn't matter. So notice that if, suppose you have an actual metric, and this is an actual gradient, then this is, of course, automatically true. Because in this case, so if, for instance, z is a gradient of function z, then then df of z is a kind of, then df of z is just equal both z square and it is equal df square. So it's kind of not really anything. It's the same thing. If it's a gradient, then you compute with respect to the same norm. So in this case, it's atomic condition automatic. But if a gradient like that, then you have this. So now there is the following proposal, which I like more, and I temporarily want to use it. But it's also not 100% satisfactory because there is one kind of open problem about this. So this is the following proposal due to Chili-Bach, and this is the following. So let's kind of substitute this condition in zero existence, this inequality. You substitute by the following thing. You say that there exists some non-symmetric metric. So there exists some kind of almost Riemannian metric, so that means it's a two tensor. There exists some two tensors, some kind of like non-symmetric field of non-symmetric bilinear form, such that it's positive definite again. So it's okay. All right, greater 0 for. So it's a positive definite, and such that if I contract G with this, then this is equal to df. So notice, if this is a usual metric, this is definition of gradient. So the only thing which you say that you don't require it to be symmetric. So you drop this condition. So it's easy to prove that this condition implies this one. So it's it's a stronger condition. But this is very, don't want to waste time, but it's a simple exercise to prove that with this condition, this perturbation is possible. So you can always perturb two Morse and in this class. So therefore, you have to perturb both G and NF and make the whole thing Morse. Kind of like any C infinity clause, you can perturb also G. So you can do it as an exercise, which is a simple exercise. And so this therefore kind of looks like better condition, but only not symmetric.
So that allows you to kind of have a...
Yeah, it allows you give like, for instance, in two-dimensional case. In two-dimensional case, you have a vector field. So if it's gradient-like vector field, it has to be always, say minimum has to be like this. But for non-symmetric, it can be kind of spiral, for instance. So it indeed, I think in two-dimensional case, it's kind of like very, very good. And anyway, so I think it's a good definition, but it's kind of, and we, for instance, in our current paper, we use it as a running definition, this thing. But the problem with this definition is that it's kind of pain each time to check that such G exists. So it's like possible, but you have to work and you don't like. So this, of course, this condition only at critical point. So away from critical points, automatically this is like you can always even pick symmetric G. So it's only at critical point this matter. So kind of like if you think and invent something fantastic, even better than this, would be good. So what we must accommodate in both things, we must accommodate. So why, for instance, I don't like to okay, obviously why I don't like to reduce to just Morse case to require, because if you reduce to Morse case, you cannot talk about families. Then you can require death birth. Okay, that's also fine. That's what we did in our book with Chilibag. But then it's also, okay, what about two-parametric family? What about 25-parametric family? So if you really want to consider parametric theory, then this is a very unpleasant condition, and therefore this would be much better. But again, not so easy to work. Maybe it's a good, but not so easy. But okay, so this is a maybe side remark, which I spent too much time with. Okay, but now I want to one more kind of generalization and point of view of, okay, so but let's admit this as a running definition, but in application which I will be consider, I never consider any kind of terrible degeneration. I would like to consider something more than both, more than Morse, because, for instance, Morse bot or something. So there are some more degenerate critical points were useful to consider, but like not too degenerate, actually in practice rarely appear. So now next kind of like upgrade of Weinstein manifold, which we want to do, I will define something which is called W block, some kind of generalization of Weinstein manifold. It will be something like Weinstein manifold with boundary with corners. So you see, let's for instance, so what is a Weinstein kind of manifold, right? For instance, you take a cotangent bundle of manifold. If M is a real manifold, this is a Weinstein manifold. But suppose M is a disk. So kind of like if you take a cotangent bundle of disk, this by itself is not a Weinstein manifold. Of course, you can make disk open, but it's not good enough because if you make it open, then kind of like you lose the boundary. You'll see it's not what you want. So you want to remember about the boundary. And so, for instance, you would like to consider object like cotangent bundle of manifold with boundary. And then, as a very natural, you'll see you kind of forced, if you start to do that, you're forced to consider not only manifold with smooth boundary, but manifold with boundary with corners, right? You know what manifold with boundary with corners. So it means that there are some points where kind of it look like this, it kind of like, so there are points where it can given by some kind of inequality. So it can look like quadrant at some point. So what is a Weinstein? What is a Weinstein? So W. Okay. So what is Weinstein manifold with boundary with corner? Okay, it's a manifold with boundary with corner. But what kind of structure near, say, boundary near corner? We want the following thing. So in this manifold near so you have a different corners. So you have we can write D1M. There is a D2M. This kind of like next corner, like in usual manifold. You can kind of enumerate corner by their depth. So you have D1, D2M, etc. And near D1M, you have a say call it one face. This D1 face, call it P1 one face. This is this vertex P2 face, D2 face, right? So it's a two face, one face, and near one face, my manifold look like P1 times some neighborhood of this manifold times 0 epsilon, right? If you consider neighborhood. Every one face of manifold with boundaries corner look like, again, manifold with corner of smaller dimension times strip. Now, if you take neighborhood of this one, it would be neighborhood of this thing. So, sorry, P1 times this. So this neighborhood, like U1, is equal to this. If you consider neighborhood of this vertex, it's equal P2 times this quadrant, right? It is times 0 epsilon square. Okay? You look. What?
So P1 is a vertex or a face?
No, P1 is a face, and P2 is a vertex. I just enumerate. So there is a boundary. There are faces of boundary. There are two faces, three faces, four faces. And neighborhood of two face is look like this face times square of this one, right? So what is a condition? Now I would like to define for Weinstein case. What? Then we say, so we have a face. So let's kind of mimic this example that we take a cotangent bundle of the manifold. Cotangent bundle of the manifold stage with boundary. So what kind of neighborhood here we have? So suppose again, say this is the face of our, so P is we have a P1 is one of the faces of M. Then what is the neighborhood of this face there? The neighborhood is equal to P1 times not 0 epsilon to first degree, but T star of 0. So it looks like T star of P1 times this. Our manifold itself look like P1 times this, and neighborhood look like T star of P1 times T star of this, right? And if you have a neighborhood of two faces, it will be T star of P2 times T star of this square. Okay? So this is a kind of definition of manifold with Weinstein manifold with boundary with cores. Like so you have this thing. And now for this manifold, when we talk about defining domain, we consider this so we consider domain like this, right? So it's and here's a kind of like main new point of view on Weinstein manifold. So as I said, like you think about Weinstein manifold as something big, infinite, or we can say this defining domain inside, and then it looks like something with boundary. But I want to forget about this boundary whatsoever. So my Weinstein manifold is a germ along skeleton, and there is no boundary. There is just germ. But if this our manifold was like say cotangent bundle of manifold with boundary, it will be germ along this manifold with boundary. So therefore, skeleton of the manifold of Weinstein manifold with boundary itself has some boundary. So Weinstein manifold with boundary with corners have boundary, but it's kind of side boundary, not vertical boundary. Right? It's a boundary coming from boundary of skeleton, not boundary because of we took of this one. Okay? Is it okay point of view, or are you confused? Okay, so anyway.
Boundary you are getting on manifold, right? Not
What?
boundary.
What?
Boundary you are getting for Weinstein manifold is in the manifold, not in.
No, but we start with so you take a Weinstein manifold with boundary with corners. So right. So what it is? So this is a so it has a boundary, but its boundary kind of only side boundary, right? So that means near each such boundary, like you also have every boundary have a so it looks like okay, maybe I should not really waste too much time with this. Okay, well, there is this notion, and let's not go into this too much. And in fact, for what is going on is not so important to think. So like if you don't like them, let's not go into this case with boundary with corner. Like think about Weinstein manifold. It will be good enough, but will be at one point it will be important to add this. You'll see. Kind of, I cannot avoid it, but mostly you can think without it.
So your skeletons itself will have some kind of
What?
boundary. So your skeletons will
Skeleton itself will have some boundary.
That is like skeleton. What do you mean by boundary of the skeleton? I mean, it can kind of drop more than.
No, it's not about the boundary of the skeleton. Yeah. No, I
So, I mean,
Yeah, otherwise, of course, right.
in this picture, there is the zero, which is the, there's a 0 epsilon cross 0 epsilon, and its boundary at the base. The tangent space level, there is no boundary.
yeah. So
So one-dimensional skeletons can have like a leaf in the graph. That's a boundary.
yeah. Well, okay. You can have a yes. Indeed, you have. So you can if you consider, for instance, like neighborhood of the thing is so this is W block, but this is again this is a fuzzy boundary. It's just in a boundary. It's a germ, and this is just pieces of boundary.
Okay. You mean by that?
Yes.
So you said actually skeleton boundary.
No, but it's not skeleton boundary. It's a boundary for manifold, but they are kind of like germ along the skeleton. Okay. Okay. So unfortunately, if I want to do it systematically, really it requires me a little bit of time because to make it precise. Okay, maybe I will kind of like do the following. I will not try to give precise definition, but I will like describe you the whole picture, how it looks like, and in a little bit impressionistic way.
But at least your skeletons are compact.
Skeleton are compact, yes. Okay, so let's see. Let's forget about this for a second, about all this manifold with boundaries corner. So we have a Weinstein manifold. And Weinstein manifold is have this function, and we want to consider more theory of this function, right? So when you probably, I'm sure you know that when you have a like Weinstein manifold, then when you pass through critical point, then this is equivalent to certain operation of handle attachment to our like Weinstein domain below, and handle attached along some isotropic manifold. Yeah, I'm kind of catastrophically cannot say what I want to say. Just kind of let me think for a second. Okay, so let me slightly switch kind of like point of view. Let's consider the following picture. So we have Weinstein manifold, and this Weinstein manifold is as we discussed, has some core, has some defining boundary, and there is this cylindrical end. So let's take this like normal Weinstein manifold. So now boundary of this Weinstein manifold, boundary in the sense of the domain, boundary of the domain as it transfers to vector field Z is a contact manifold. So the form lambda restricted to dw is a contact form. Now suppose we have in the boundary you have a Legendrian submanifold. So lambda is a Legendrian submanifold in boundary. Then there is a well-defined operation of Lagrangian handle attachment. So that means you can take a disk and you take a cotangent bundle of this disk. And again, think about this cotangent bundle of this disk as this like manifold with this. Now I want to think about it, a manifold with kind of like Weinstein manifold with boundary. And now I kind of attach this thing to that. Okay, so now you need to understand what does it mean, this attachment, right? So you attach, and then this, in fact, this boundary is not there, because this object handle is in fact kind of just again germ only along the disk. So this is a well-defined boundary, and this kind of fuzzy boundary because it's just germ. So this is a boundary. I kind of like I said it boundary, but again this is a kind of fuzzy boundary. So when I attached, there is this boundary doesn't exist. This boundary doesn't exist, but in order for me to attach, I need to do a little bit adjustment of Liouville vector field, because I want to make Liouville vector field in such a way that it would be, so here you have a canonical Liouville vector field, and here you had a canonical Liouville vector field there. And here they do not coincide. But there is a very kind of like, it's a kind of two-dimensional problem of attaching, because when you attach, so here, remember, in our handle, neighborhood of the boundary look like we have the t star of ddn times t star of 0 epsilon, right, of this interval. And here we had a like two, for what is the contact structure here? Say, let's call the PDQ here, and plus, say, coordinate here denoted by t, and coordinate, dual coordinate by s. So I have plus s dt form there. So our original vector field was, at this part, was this PDP, Liouville vector field, plus t d over dt, plus s d over ds. This was our original field. But when we glue, it glue here with field which equal p of dp, but here t d over dt is it s, or maybe I need to put that, because here it was dual to form s dt, and from this side it's dual to form minus t ds, which is the same thing in terms of symplectic primitive. So when I glue symplectic structure because it's kind of the same thing, but I don't glue Liouville field, Liouville form. And so therefore I need to have some kind of adjustment between in this part between this Liouville form corresponding minus TDC and SDT. But that's just two-dimensional question on the plane, which is kind of very easy. You do some kind of picture like this, kind of like with the, yeah, I can write explicit formula for this interpolation here, and that's how it attaches. So this is called operation of like attaching this handle. But this operation, in fact, much more general operation. This operation, in fact, when you have a manifold with boundary, with corner, for instance, manifold with boundary, and then when you have a boundary, so boundary itself inside contain, like here, it contains T star of ddn. It contains some what I call nucleus, some Weinstein domain of smaller dimension. And in the neighborhood of this look like this nucleus, you will form nucleus, and plus like TDS. And if I want to attach, so if I have this block and have this boundary, and I want to, and then I have another Weinstein manifold, and I would like to kind of attach it vertically. The whole thing which I need to do is change TDS by SDT. So it's kind of this operation which you do by attaching handle is in fact much more general operation when you can take this what I call W block and kind of do it with each other and attach it to each other. So therefore, that kind of I would like to think about Weinstein manifold, like present them as what I call double. So there are W blocks, and out of W blocks, I want to make W buildings. A W building is some kind of Lego construction. So suppose you have this W blocks, kind of many W blocks. And then out of these W blocks, you can make W building by just kind of like piecing it like this. So you take if you have one block and another, and here you can, if you have a boundary face, if you can realize this boundary face as in this kind of vertical boundary, you can attach it. Then if you have something with boundary with corner, and then you can now attach it this way. So there is this kind of like picture which generalized handle body attachment, which is very convenient. So you can like build any Weinstein manifold as this Lego building. And what is kind of nice about this thing, that this construction can be done upside down or from down up. Because you see, like you just think about Lego, and kind of course you can, if you try, you constructed something and you want to destroy it from the bottom, it's a little bit difficult, but still you can. There is a first layer, and you can like remove like somebody holding, but then you remove first layer and you get next one, or you can remove, or you can instead start to dismantling from the top. So there is all these blocks have certain order, and they build this way, right? It's when you have the handle body attachment, it's a handle body attachment kind of looks like this, except that there is a following problem. So when you have a like you attach one handle, and then you want to attach another handle, and this another handle kind of not attached in good way to this two. It's kind of like the way how it attached, it kind of go here, go back, and kind of there is a absolutely kind of like so extremely inconvenient to work with handle attachment. So you can again build them from bottom to top, but kind of in other dismantle in opposite directions completely impossible. So okay, so that's what I'm saying. That's why I like this kind of philosophy, and I'll explain why this for my purpose is better. Okay, but
so formally, is it a partial order or a total order?
okay, the way how we define it as a total order. But maybe this is not so good. Maybe it's better to but kind of like the way how we do it, there are, if you do it as a partial order, some problem arises, and kind of we didn't want to deal with that. Okay.
So I think when you attach these vertical blocks, let's say at some point of time you put a horizontal block on the top of vertical, you will have to deal with this interpolation.
Yeah. So the problem is the following. So suppose you put one first vertical block, and now you want to put second. And suppose originally this was just Legendrian thing, Legendrian attach Legendrian. So now I need this Legendrian first to deform Legendrian in very special position. So like when I need to control how the Legendrian, what happens when you pass from one block to another. Okay, why kind of I want all this? So I want this for the following purposes. So the theorem which I want to prove is the following. So you see, for instance, you start, say, with ball, and you attach some bunch of handle along Legendrian, and you want to look what is the skeleton. Well, in the ball was our Liouville field was kind of like, for instance, trivial. And what would be skeleton here? So what would be skeleton of Weinstein manifold when you just attach one handle? So it was the core of this, and plus cone over the Liouville cone over this one, right? So the skeleton will be this kind of drop. But this is extremely bad skeleton, because this singularity really just encode itself all this Legendrian knot. All topology of Legendrian knot is hidden in this. So it looks nice like only one singular point, but extremely bad singularity. So it's not good. So we would like to have singularity so simple, maybe more singularity, but have them so simple that just looking at singularity we understand what's going on, not just go into symplectic geometry for understanding singularity. So how we can change this? Well, let's change. Suppose I can redo this thing to do that. You said, well, let's change our ball by cotangent bundle of the disk. So now I want to think about this as a manifold with boundary with boundary. So this was my object, and now I attach a handle. But now in this block my Liouville field is just PDP. So now the skeleton is just this plus disk. Okay. So what now singularity? Let's consider in this case what singularity of this object. Okay, that depends. This is precisely front projection of this disk. So this Liouville cone is a front projection of this disk. So singularity, whatever this front projection was some kind of front projection. Whatever. Was some front projection, and now we attach this along this front projection. But I don't like it's kind of too complicated front projection. I don't want this either. So I would like some kind of more simple singularity. So, for instance, would be very nice that singularity which I got, that I get actually this embedding. If I get embedding, that what would be singularity? Singularity would be just this, and no more than this. It will be if you have a Lagrangian and its front projection is embedded, then locally near singular point it just look like product of T times Rn minus 1, right? So this kind of next object which we want to consider, so one object we consider is just Rn, and next object we want to consider in Rn take a half space and take a kind of Rn two Lagrangian which intersect along this Rn minus 1, right? So it's a product of just T figure with like complementary Lagrangian, right? So it's the next one. This is not quite sufficient because I cannot guarantee that I always getting embedded Lagrangian. Okay, are you with me still?
No, I just can't understand.
Okay, let's start new life. A new life will be like what was before life was green, now white. So I'm kind of like, we'll try to explain the same thing slightly from other end. So I'm trying to classify singularity of skeleton of Weinstein manifold. So like best possible singularity, you take a cotangent bundle of Dn of Rn, right? And then skeleton is really smooth. This is our skeleton, just Rn. Okay, this is too simple. So kind of next good thing we take a T star of Rn, and then suppose you have a Legendrian lambda in the boundary, and front projection of this Legendrian is a front. And this is like front projection of this Legendrian and just embedded hyperplane, right? So then skeleton in this case is just look like T figure and times maybe times Rn minus 1. But now I cannot avoid, of course, this to be immersion, right? So it's possible that I have in projection I have a two Lagrangian intersection, and then what would be corresponding picture? Picture will be you have this Lagrangian plane. You have a one Lagrangian kind of look like this, which is a conormal of this, which is conormal of this. Then you have another Lagrangian, and you have a conormal of this. So these two Lagrangian do not intersect except at this point, right? So this is also kind of next picture which I cannot avoid and will be one of my singularity. Now let's kind of look at, let me restrict for the moment just to dimension 4 symplectic manifold. So scalar are two-dimensional. So if scalar are two-dimensional, we already have a 1 type, 2 type, 3 type, and then we'll have to have one more time, and that's it. And this one more time is the following. First of all, what are scalar in one-dimensional case? What are possibilities? What? Okay, either line or again this T, right? Because Legendrian could be point. So that means if you take just cotangent bundle of strip and attach a handle, then this is precisely you get the singularity, right? So you have this singularity. So therefore, now suppose you have already Weinstein kind of two-dimensional manifold realized as a neighborhood. So yeah, I'm attaching vertically to my cotangent bundle, I am attaching already Weinstein manifold of high dimension, and I am attaching along this two-dimensional Weinstein manifold, right? And so therefore, I need to take a boundary. On the boundary, I need to take something, and this something has already scalar with this singularity. And now I need to project this. So I need to see what happens if I take a cotangent bundle of R2, and in unit cotangent bundle of R2, I consider this Lagrangian graph, this which is a skeleton of something. And what happens when I project this thing to the base? So what would be projection? What will be projection of T figure, of Legendrian T figure? What will be its projection to the plane? Yeah, not cuspidal. So it will be kind of look. So it will be okay. So this piece will project to line, and this piece where project? It will project as a thing, but it's not cuspidal, quadratic. It's a quadratic tangency. So it's a piece of parabola. So therefore you need to next picture which we want to consider is so you take a plane. On the plane you take a line, then you take a half of parabola, and take a conormal to this. I mean, you take a half conormal for this, and take a quarter conormal for this. Okay, I'm drawing this, it's kind of like, sorry, you take a quarter conormal for this. Okay, sorry. So you take this thing, you take a conormal for this, I draw this, then you take this one and you take a conormal for this. They kind of look like this. So it will be like quarter of plane, and here is attached kind of transversely here, everywhere, but as it comes to the point on the skeleton, you get a quadratic tangency. So that's it. Turns out, so this is a all list in dimension 2. now there exists one more kind of orientation thing. So this stuff coming with some sign. Because, like, imagine that suppose we have this our unit cotangent bundle, right? And there we had this our Legendrian, and you have this T figure. And we were projecting this T figure along some direction of the fiber. Direction of the fiber was kind of transverse to both when we were projecting. But this direction could be like this, or it could be like this. And this gives us 3 Lagrangian lines in the plane. And do you know that 3 Lagrangian lines in the plane have Maslov index? Have you heard this? So suppose you take a symplectic space. In symplectic space, you take a 2 Lagrangian pure linear algebra. You take a 2 Lagrangian plane. So any 2 Lagrangian plane give you kind of like coordinate system. There is by symplectic isomorphism, you can put any 2 Lagrangian plane to any 2 other if it transverse. So I can think that this 2 Lagrangian plane are like x and y kind of Lagrangian plane, right? So now you have a 3rd Lagrangian plane. And suppose this 3rd Lagrangian plane is this 3rd Lagrangian plane, for instance, is like transverse to both, right? Then you can think about this as a graph, any Lagrangian, a graph of differential of function. And because it's linear, it's a graph of quadratic form. So in this case, in this one-dimensional case, this quadratic form is either plus x squared or minus x squared, precisely kind of depending which one I take. So therefore, you have this, and here you have a 2 Lagrangian plane, and you have a 3rd one. And then we can make the following assumption. So suppose this is like base Lagrangian. This is a direction of projection. And this is a kind of 2nd Lagrangian which we project. And we just think about this as a coordinate system and think about this one as a graph of some quadratic form. And we think about, is it plus x squared or minus x squared? So if it's plus x squared, then we say this is a positive singularity. If minus x squared, it's negative singularity. So let's assume once forever that we require all singularity whenever they appear always be positive. So just kind of if I have time, I'll tell you what to do with negative singularity. But let's assume that it's just requirement always that we require in all such things projection to be positive singularity. Okay, so now I can really already give you definition. So like I'll give you, and then after that I try to explain how this could be proven. You formulate some theorem. So definition, positive arboreal singularity. So let's consider let T will be rooted 3. So you have some root, and then you have some growing beautiful tree out of this root. So you start with rooted tree. And with this rooted tree, I will like to associate some very particular Lagrangian singularity. And this Lagrangian singularity will be in, so suppose this thing has a, say, n plus 1 vertices. Suppose you have a tree with n plus 1 vertices, then I will describe you Lagrangian singularity in kind of cotangent bundle of Rn. This thing.
By rooted tree, you mean you specify a vertex?
Yeah, there's a root. It grows, not, you know, there is some tree which kind of grows from many roots. But okay.
The valence is 3 at every place other than the root.
The valences, just, yeah, valences, it's kind of binary tree. It's kind of like, you have the stream. Okay, so now how you transform this root with singularity. And moreover, it will be unique up to symplectomorphism singularity. The singularity have a normal model that all of them will be just kind of one forever. There's no kind of model in nothing. So let's start. Let's kind of like, instead of like giving immediately the syntactic definition, I'll just start kind of building this tree and just show you what it is. Okay, so let's take this tree. So for this tree, as you can guess, it will be it will be point. it will be. I will associate Lagrange. So here I associate Lagrangian in cotangent bundle of Rn, or you can also have the same thing in for every n plus k, but in this case I just multiply by Rk. Right? So that means that this but by definition, when I take a 1 point, I get something in T star of R0. So it's just point. But you can multiply the whole thing also by Rk and have just Rk in T star of Rk. It's kind of the same singularity. Okay, so now you have 2 points. You have 2 points connected by this tree, and then this picture appears first time in T star of R in 2-dimensional case, and that's what you do. You take a R, take already this thing which correspond to our previous singularity as a Legendrian there, and take it projection there, and take kind of positive project, but in this case a positive nothing. So in this case you get this singularity. So this is a singularity which corresponds to this one. So now we want to take this tree. So it's one root, but from root could already this grow, right? Suppose you take this tree. So this tree happened in the case again R2. So what do I do? I take again I take a yes I take a R2. Take cotangent bundle of R2, and in unit cotangent bundle of R2, I take 2 Legendrian which correspond to previous singularity, which is a kind of like line. So therefore, you take a 2 Legendrian line there, but you request that this 2 Legendrian line intersects the same fiber, not disjoint, but intersects the same fiber. And therefore, you project them, and you get this picture which I was drawing before. Yeah. Okay, now you can guess what, for instance, what happened after that break. You have this one. So what then you have? Take this tree. then what you associate with this tree? What?
Then you have the train track.
Yeah. So then you take this is in 2 dimension, and in the boundary you have a Legendrian which corresponds to this tree, which is just that. And now you project, and you get this what we was drawing before, right? But you insist here that it's a positive configuration. So only here you would have to have choice, but I always insist on positivity. Okay? Yeah, and it like inductively it's clear what we're doing, right? That's precisely what we're doing. So we take.
So you're making sure that it goes to a specific side of the thing, right? By choosing a positive symbol. It's not.
Yeah, you're choosing this against this. Okay, let's make a break.
So otherwise that extra quadratic projection that will go downwards, right? If we are taking a negative.
Okay. Are you asking downward? So,
Like
okay.
that
Where the plus correspond to going downward or upward or minus? That's we have to compute again. So, okay. So that.
I'm asking that type of picture will come if we are taking.
Yes. Right. So it's switch, but kind of which is which. I have to more accurately write what the coordinate axis. So let me kind of repeat this list of arboreal singularity. So as I said, so it's defined inductively. So we have a. So suppose we already. So first of all, there is this kind of like what is called kind of IN trees. So there's trees which really kind of like extremely nobody really cared well about these trees. So they grow like this. So take these trees, and so singularity for this one, in some sense it's a main singularity, but they're simpler. So again, how this singularity defined? So suppose you already like. So say I always forgot what is a k? Is it like it's a k point or k plus 1 point? Okay, k plus 1 point. Okay. Well, anyway, so okay. So there's this ak already we know, and then how do we define like or say ak minus 1 we know, and how do we can define ak? So we take this next whatever rk. So take rk, yes. Take rk, and then you have a unit cotangent bundle of this like st star of rk, and st star of rk. There we can put consider Legendrian. So you can take our Lagrangian singularity ak minus 1 and put this Lagrangian singularity as realized as a Legendrian piece inside this bundle. And this unit cotangent bundle, it comes with a Legendrian fibration, which are intersection with cotangent fibers. So there are family of Legendrian plane, and we put kind of our previous singularity. We put there ak minus 1 there as a Legendrian, and we notice the following thing, that if you have a ak singularity, that you at singular point there are always two tangent Lagrangian plane intersecting along codimension 1. Always you have this pair. Sorry. You have this pair of this plane because like each time, like for instance, third time, so first time you have this, and next time, as we remember, we had this already picture. So we have two transverse, but third one at this point already becoming tangent, because it's not possible to have at this pure algebra. You cannot have a 3 Lagrangian plane and each 2 of them intersect along something codimension 1. Only 2 maximum. So there are always kind of, even you have more branches here, but there are always 2 distinct directions, and there is a third direction. Okay? And then kind of everything is just, in fact, reduced to dimension 2. Like in dimension 2, you get kind of like reduction of this Legendrian, which give me line, and plus you have another 2 lines. So this is a fiber. This is a kind of like base, and this is like other kind of piece of this arboreal singularity. So the side piece, and you want that in this coordinate system base fiber, this is a positive definite quadratic form. Okay? So you have this insist. This is called positive arboreal singularity. So now this is for A. If you have if this thing, for instance, branched instead, then what do you do? That means, okay, you already know what the singularity, and you want to have this. So for this, it means that you have so now this is not local, right? You take 2 singularities there, and you want this singularity transversely be in different point, but such that their intersection along fiber transversely intersect. And the kind of whatever you allow under this transverse intersection, you can realize that and get. Okay, so, but this is kind of like most interesting thing happen kind of when you take just growth in this AN direction, other are just kind of combination of that. So, okay, so now the theorem, like what we proved is the following. Okay, so there is in fact, other type of singularity which may be useful to consider. I kind of like I fought hard against them, and kind of like of course another originally proposed them, but I tried to get rid of them and I succeeded. But then now we kind of like finishing this paper in parametric version of this, and then kind of like it became getting rid of this extra singularity became a nightmare. And so maybe he's correct. There should be systematic introduced. Okay. So what is this extra singularity? So we want to have the following thing. So suppose, so as I said, if you have a Rn, like for instance R2, and you put this line, then you get this kind of simple A2 singularity. But what if you put not line, but you put just compact interval? Then you have this point, and this point at this point is kind of some. So picture is not. It's not neighborhood of this point. It's not diffeomorphic to neighborhood of this point. Right? So you would like to avoid this. And what okay. So and I told you how I kind of managed to avoid that and why this is not turns out to be a good idea in parametric version. So, but now kind of you can understand. So, how you want to extend? You want to extend this boundary point, but unfortunately, this boundary point iterate because you got this singularity, but now you take this singularity and take a projection of it, and then you get another things, right? So this is kind of like you get kind of another class of this border type, this arboreal singularity. Okay, so maybe they have a right to exist.
This is the reason why you really want Weinstein manifolds with corners. I mean, the depth of the corner keeps increasing.
Yeah, in some sense, yes. So like what I can trade I can trade instead of creating all this interior corner, I can realize see them explicitly as a kind of some extra faces on the boundary, right? So in some sense, you're absolutely right. So for instance, I had this. Suppose even I started with a ball, and four-dimensional ball, and I attach a handle. No, okay. Suppose you, even this, you take this one and attach a handle. So already in this situation, you can do is the following step. Either you take honest cotangent bundle of the disk, and then attach this handle, and then you get kind of like beautiful arboreal singularity before. But you created corner. So of course, instead of creating corner, you could not create corner, but you just consider this Weinstein structure inside such that attractor is not going to the boundary, but inside. So it kind of here it look Liouville vector field like this, but here it just kind of look like radial vector field. So attractor is this interval. But then you create this interior corner. And then also problem arises when you attach subcritical handle. So suppose you attach subcritical handle of index 1, right? And then of course when you attach subcritical handle of index 1, then it's the same. You can replace attaching subcritical handle of index 1 as attaching some strip, some Lagrangian strip. But if you attach Lagrangian strip, you create this corner. So you can avoid it. You say, well, instead of attaching Lagrangian strip, you do the following thing. You attach disk with a hole, kind of. Attaching disk with a hole is the same as attaching kind of one handle. With two holes, kind of, right? You want to attach disk with two holes, it's the same as attaching with one handle. And then you can avoid it. So there is a kind of like stupid trick which allows you to do, and you prove the theorem that you don't need them in this expense. But then you kind of pay this price. But then, as I said, in parametric version, this become kind of, it's possible, but the following thing happens. So you would like also classify all bifurcations. And if you allow the singularity, then list of bifurcations still quite simple. But if you require that each time, even in bifurcation, the singularity do not appear, then bifurcations themselves become grown in very, very long list, which kind of course, not good. Okay, because you have to, as a one bifurcation, you can call some sequence as a. Okay, so now let me kind of like explain a little bit where the positivity. So what are the steps of the proof? So there are three major steps of the proof. One, before anything arboreal, you would like to, you have this handle body. Suppose, so you start at Weinstein manifold, and this Weinstein manifold have this like handle body presentation. That's by definition of Weinstein. So first you would like to rebuild handle body presentation in this like cotangent building structure as I was referring to. So you do the following. So first you started with kind of like okay, let's ignore subcritical handle. It's kind of like you have to do something with them, but it's not so essential. Let's suppose we just always attach handle of index n. Yes, so you attach one handle. So far, kind of so good. This is a building. So you just precise. But now you have another Legendrian, right? And you would like to think about this as attaching of this block with corners. How you can kind of understand this block with corners? So what that means? We have this Legendrian, and so like our Legendrian original was attached along, say, our original handle was attached along this Legendrian, right? And this Legendrian itself, inside contact manifold, has Weinstein neighborhood. I call it Weinstein ribbon. We can thicken Legendrian to just take a two-dimensional ribbon tangent to contact structure along the Legendrian, because neighborhood of Legendrian is the same as the neighborhood of zero section in one jet space. And therefore, it is the same as a T star of this Sn minus 1 times R. And inside this, you have a T star of Sn minus 1 times 0. So in this, like for instance, if it's a one-dimensional Legendrian, you have a like two-dimensional annulus, kind of Weinstein annulus inside this boundary. So now the other Legendrian, so we have this Legendrian, and in our three-dimensional contact manifold, it has some tubular neighborhood. How to draw it? Okay, so there is this kind of this Legendrian, and then there exists a tubular neighborhood of this Legendrian. And on the boundary of this Legendrian, you have this boundary of this ribbon, right? So there is this like two-dimensional, three-dimensional solid torus, and in three-dimensional solid torus, you had a two-dimensional kind of annulus, which is our core. And the other Legendrian, which kind of along which the second handle attached, it come here and kind of like in controlled way penetrate to the handle. But this kind of like corner structure, it requires that other Legendrian actually enter this neighborhood as a continuation of the fiber on this cotangent ribbon. So you want to kind of deform our Legendrian in such a way that it would enter like this, and then it would go already as a Legendrian on the boundary. Like everything going in this two-dimensional kind of direction, kind of like, okay? So that's what we need to arrange. That's what this structure means. And well, that's possible to do this. There's kind of some work, and that's possible to do. So after that, we got this building structure. And now we would like to, next step. So suppose first we have just two blocks. We have one block. This is just cotangent bundle of Dn. Everything is perfect. Core is just Dn. Now you attach second one. And you get some Legendrian. If this Legendrian emerged projection, then it's, and say with transverse intersection, then by definition, this is a arboreal situation. So now we need to, but this is not true. We don't know that it can project with terrible singularities. Right? So how to achieve this? And here come something which we call some tectonic activity. So we will do some kind of like, okay, so this is the following thing. So here's a claim. So let's call, so suppose you have a Lagrangian. And now I will consider Lagrangian which will be piecewise smooth which I will be calling Ricci. So Ricci Lagrangian is the following thing. Like one-dimensional Ricci Lagrangian besides smooth one is just that. Two-dimensional additional kind of Ricci Lagrangian, it can have this, the same singularity times R, or it can have a product of these two things, etc. So it's like this, that's our Ricci singularity. So that's what happened in the following way. So suppose you have a plane, and you take a line and you kind of fold it. So you get this ridge, but then you can have this one, and you have this additional folding along this one, but folding along this point should be precisely like product of two folding. That's what it is. So the theorem which we're proving is the following. So you take our suppose you have a Lagrangian, and think about this. In fact, it's not Lagrangian. It is our Legendrian which is sitting in unit cotangent bundle. And then there exists another field of Lagrangian which are like Legendrian fiber. So for this Legendrian which sit in unit cotangent bundle, so you have unit cotangent bundle that you have a sitting Legendrian, and you have this field of Legendrian. And we want to achieve some kind of degree of transversality there, right? That singularity. If it transverse, then projection non-singular. So it amounts to the following problem. So you have a Lagrangian in cotangent bundle, like zero section, and what I call Legendrian plane field. You have any Legendrian plane field, let's call it lambda or mu. So mu is a field of Lagrangian plane in cotangent bundle along zero section. So for instance, you can take a normal vector field, it would be kind of perfectly transverse. But if you take an arbitrary plane field, then it have a kind of unpredictable singularity, right, tangency. So the statement is the following. You can kind of crack, you can do earthquake. So, okay, so first I formulate in kind of ideal way, kind of the way how I would like to formulate, but unfortunately it's wrong. You know that I can tell you this kind of joke, which actually I use as in my kind of in this presentation. It's like it's a real story. So kind of like in school was old teacher teaching some class in mathematics, teaching how to add fractions. And this teaching was teaching that you should separately add numerator and denominator. And then somebody was present in the class, was listening, and says, what are you talking about after class? And it was an old experienced teacher, and she said, well, I know this is wrong, but for children it's much easier to understand. So that's what I'm doing now. Okay, so what I will say will be wrong, but I correct how it should be correct. So what I want to say is the following. So you take this field, and now I want to do the following thing. I want to crack this Lagrangian, make it deform, and actually see by C0 small deformation of this of tangent plane, deform it to make it kind of rigid with this type of rigid, but in such a way that this rigid Lagrangian after that one becoming all strata becoming transverse to this polarization. So you can crack them to become transverse. So unfortunately, maybe this is true, but we just cannot prove this. And we proved slightly slightly weaker statement. So this is indeed you can achieve it, but you achieve it not just by C0 small perturbation, like in most places it's C0 small perturbation, but also you allow what we call some kind of wrinkling. So kind of like you also create. So in some places you keep it almost horizontal, but kind of you have to in fact flip direction almost 180 degree. So but anyway, but singularity of this thing still remain just rigid. So in other rigid it kind of can be complicated rigid, and this extra additional rigid is just simple just product of like fold type thing. So maybe they are not necessary, but that's kind of what. So that's what we proved. And okay, so therefore all now problem, therefore in kind of arborealization is just about how to arborealize projection of these rigid singularities. But rigid singularities are simple enough, and so you can really inductively over this depth of the ridge change them to arboreal. So this is what we did.
These extra singularities are wrinkles?
What?
These extra singularities are wrinkles that you require?
Yeah, so this is a kind of analogs of wrinkles.
But they're not real wrinkles, right? Because the
Yeah,
points
okay. To make them instead of wrinkle kind of like double folds or something.
Okay.
Okay.
Then it's rigid.
Yes, it is. Okay, so now there is one more step, and this is okay. So that's how you deal with this one. We have a 2 edge. Now suppose we need to add already. So this is already everything arboreal here, and we adding one cotangent block. And first you just arrange everything that here is like in this building form, as I said before, and you make this rigid with respect to both projection. No. So, okay, so now here's a problem which arises. That's why it's difficult to deal with arboreal singularity other than positive. Why this positivity condition come in really most important way. So suppose you have 2 blocks, and now you first have your Legendrian, and first and this Legendrian kind of near this boundary look like cylindrical, everything kind of standard as we're coming here. And you make this Legendrian to be first rigid and then arboreal with respect to this projection. But then here you already connected this arboreal, and now you project already the singular arboreal object. You need to project in this direction. And then it's not really arboreal. So that's kind of like you lose the transversality. There's absolutely no guarantee that its projection, this your arboreal singularity which you created. This one then after that projection to this direction, they becoming arboreal, becoming transverse and then therefore arboreal. And the kind of crucial lemma that if they are positive, then this is true. So therefore, it guarantee as long as you achieve transversality, not transversality, but with arboreal singularity in this direction, and they are positive, and there is a global polarization, then you can, it's automatically guarantee that this singularity, when you project them in this part to this block, then they remain transverse, therefore.
Describe the problem again, sorry. Can you describe the problem again? Here you have two Legendrians.
So you have two blocks, and you have another Legendrian. And you just first look the part of this Legendrian which kind of coming to this one. And in this corner, it's already kind of standard of the product. And so you just took this thing and apply your procedure, and you get this arboreal projection. And now, in this corner part, you want to see how this part projected this direction. And if the singularity, if the arboreal singularity was not positive with respect to this polarization, then you cannot guarantee that it will be transverse when you project along this direction. But this condition of positivity does guarantee this.
Maybe if you tell that why this problem doesn't come in 4 dimensions, the picture then will be clearer.
Yeah, I think it could be understood.
Somehow this positivity means that this Legendrian is graphical with respect to both of the Lagrangian planes, both of the Lagrangian fibers.
Yes. Why it's come to just one second. In dimension 4, it probably doesn't exist, this problem, because too small dimension. Because you see, yeah, because this positivity applied to kind of like to interface. So interface is kind of one-dimensional. So this first problem first time appear in dimension 6. So it's not.
Just backing up a little bit. So in this rigidification of your Lagrangian, this is a C0 small deformation, right?
It's yeah. So it's a zero small deformation, but almost C1 small. Because it's kind of C1 small everywhere, except that we created this kind of double fold. So it is kind of controllable. And so, yes. But important that this new Lagrangian kind of like, it's in some kind of like, so it's obvious that like this new rigid Lagrangian you can make as a skeleton of the thing. It's kind of, it's very homotopic structure because.
So what's the key idea there? How does one achieve this?
What?
This rigidification?
Yeah, I can explain. So let's.
These are just a function from the smooth manifold.
What?
I have just a function from
What is function? No, it's a field of Lagrangian.
No, I'm saying that, I'm saying that you are kind of defining some particular kind of singularity of intersection of Lagrangians.
Yes.
Intersection of Lagrangians.
Yes.
But I'm saying that in one jet space, intersection of zero section with zero section is a singularity of functions. So there you can simplify singularity.
Say it again.
Okay, I ask you.
No, but I really don't understand what you say.
Okay, let me think.
So, like at first, so by the way, I kind of like I want to say the following. So this, at first, I was extremely excited about the whole Ricci idea, which in general looks to me as a kind of like fantastic advance in singularity theory in general, because like also you can very much apply the same idea in general singularity theory, and so you always can reduce to singularity of this in this rigid type. And so you could say, wow, so this is it's a kind of something, because like in general singularity is completely kind of like undescribable, and here they look like very nice. And in some sense, yes, but what is the kind of like where the catch?
That's what I'm precisely trying to.
So catch is false. So let's look at this picture. So you have how is everything classified? So you have this so you have standard quadrant. So our singularity is a standard quadrant, and then in this standard quadrant you have a one more Lagrangian to which is transversal. So which is this positive, which is and this thing is quadratic form, non-degenerate quadratic form. And this quadratic form is also transversal to each strata. So that means that you have a quadratic form on Rn such that on every coordinate subspace is not degenerate. So the question, what is the classification of quadratic form? What is the space of quadratic? Like take in the space of all quadratic form, consider all these chambers. You have a lot of chambers where this kind of quadratic form which are have a non-degenerate to every space. So so it's kind of like enormous classification thing, and all of them, they are not equivalent. For instance, I take this like plane and slightly church, then of course you don't have an isomorphism, so they're not diffeomorphic. So it's kind of reminiscent. So you know that there exists this like Tom theorem about topological classification of smooth singularities. Tom, I think, but then some other people. But anyways, like a equisingularity theory that, well, you cannot classify singularity smoothly, but like topologically you can. And this is kind of like some version of this. So it gives you some kind of maybe more descriptive topological classification of the singularity in terms of this chamber in this Lagrangian case. But it's still kind of enormous. It's so kind of like so it's not really so like and this positivity condition kind of like extract one particular chamber there. No, I'm wrong. No. It's no. It's not about this. This positivity condition. Sorry. It's complete nonsense. There's a positive condition about our arboreal thing, but this our ridge, of course, this kind of how they with respect to sign, we cannot control that. No. I said too much. So okay. So how we prove it?
What's the key idea?
Yeah, is it the following? Yeah, what you said?
Yeah, so that you're taking transfers at each like breaking point, you're taking this union to be transfers to it. So how is that impossible?
How this
Like,
impossible?
No, how is that like? How are you doing that regionalization thing that sir said?
Okay, let me as I can I will answer this. So I will start proving. Yes. So we have our distribution. So let's just kind of like do something extremely stupid. So let's just cover it by some coordinate neighborhood, and I will be working in this neighborhood, and I'll explain how you patch this neighborhood later. So take a one coordinate neighborhood, that's just Rn, and you have a plane distribution. Of course, over Rn, every distribution is homotopic to any two distribution homotopic, right? So there exists deformation of this distribution over this disk into vertical one, into the one which transverse. Okay. Now I am saying this distribution can be done in the following controlled way. Not just any deformation, but I want the following thing. I want to find some set. I want to find some set of like direction given by kind of L1, L2, L. So what I want to do the following. So I am adding. So I each time I start to rotate. So this deformation, I want that I rotate every Lagrangian only in some rank 1 direction. So I only changing, like if you think about the quadratic form, I only change rank 1 quadratic form. The same rank 1 quadratic form, but maybe with different coefficient to all field of this Lagrangian plane. So I first add some kind of a of x L1 square to all of them, etc. So that's what. So I have this. So it's kind of my first claim, and which is a like trivial claim, that every deformation can be realized as a just composition of several rotation in rank 1 dimension. That's kind of fancy. So now let's take just one of the first rotation. So I take this. So you start with in opposite direction. You start vertical one and rotate to yours. So let's take this rotation. So we rotate along L1 square, and I'm rotating, and then suddenly it becomes tangent. And at this moment, so what does that mean? Because everything change just in one direction, then this like you hear it was transverse, and then it switched to this one. So now I want to. So first, I would like to do this cracking. The first I do this cracking formally. So what we call we create some tectonic field. So it kind of not. So what I will do, I will change my zero section in the field of Lagrangian, which are themselves not tangent to any Lagrangian, but they are Lagrangian plane and like very close to zero section. I should just a little bit perturbed. And what I'm doing, I'm watching here that in this direction, so we were positively transverse, and suddenly at this point negatively. So at this point I'm jump. I change my field to kind of you make it discontinuous along this one. So it was you see, it was tangent kind of like at some point, but then because I made this jump in this direction, now it kind of like when it changed, nothing happened, right? Okay, so therefore, so I created this tectonic field, and I claim that now you can continue it, which is you have to kind of care, but so you take a second one, and then you get the second crack. So first what you create this tectonic field, which is now transverse, and it has these cracks along certain hypersurfaces.
These can intersect.
Yes, this intersect. But here there is a problem, because it's only formal thing. And I would like to make this kind of deformation like as a general integrable. And this only possible, so there is a, remember I had this direction of like L1, L2. And this direction of L1, L2 not necessarily tangent to crack. So if my like kernel of linear form L1 will be tangent to crack, then of course I can like integrate this, because in one-dimensional case it could be integrated. But if it go in another direction, I cannot do this.
So wiggle the
Yeah.
Wiggle
So anyway, so what we do, we kind of I achieve this kind of like make them tangent, but at expense of elsewhere we create this kind of like wrinkle, and so something like this. So okay, so this is this procedure, and you see what is great about tectonic fields when C0 small, and therefore you can work with them with functions. So I did it on one thing, and then I take a next, and I just adding new one. So and I could make it in arbitrary small epsilon scale, this one. And in the next time I will do this crack like 10 times smaller, and hence I will not destroy what I did first. Yeah, so this kind of looks like nice thing, but I'm not really sure that it's kind of useful for much. Kind of it work for this. I really would like to see this applied to something, because I think it's kind of interesting idea, because you can kind of in some sense regularize singularity, and pretty not only in this case but in many other contexts. You can regularize them in some way to be observable. But for what? So in some sense, you see, you can say, well, every smooth map can be approximated by piecewise linear, right? And then, okay, so it's a good to say, but so what? So this is a little bit in this direction, kind of a little bit more, because it's piecewise smooth, but with very kind of concrete singularity, but it's maybe not such a big advantage. Okay, so I think, okay, any questions?
So for Weinstein manifold, you constructed this tree, right? Rooted tree. Domain, sorry, for Weinstein domain you constructed this. If you consider its deformation in terms of, let's say, Weinstein structures, then is it worked out how the tree changes?
No, yes, so how it works, kind of thing. Yeah, no, but it's a singularity, it's the same singularities, but what kind of bifurcation? It's kind of like in fact, okay. No, you can give us a list of bifurcations, but it's a maybe, yeah, there is a list of bifurcations. So we didn't really make it public yet, because as I said, so first list was too long because we were fighting with this boundary backbone. But now it's kind of like look more reasonable, but still I'm not very happy with kind of like, so maybe it could be simplified to some kind of simpler list. So you see, what I'm kind of like, maybe I've finished with the last thing. So in fact, out of all singularity, for us, most important and most essential are just two things. You consider like this, kind of along this. So you have something attached along embedded on or possibly immersed object. Then you have this singularity either of like this type or kind of this type, right? So you have this two type singularity. So suppose like forget about anything. So all this kind of stuff about like H principle of everything, they in many cases, very geometrically interested, allows to reduce skeleton to just this singularity. So it's all singularity is just of this type. So if, for instance, there is some meaningful theory for Weinstein manifold with these singularities, it would be extremely interesting, because then it would some kind of let this in the area of kind of combinatorics. So I can give you kind of example. So suppose you want to prove again nearby Lagrangian conjecture. And what is nearby Lagrangian conjecture? It says that if you have a Lagrangian in the class, exact Lagrangian cotangent bundle of say of sphere, then it has to be zero section up to. So it's already proven that this Lagrangian have to be, say, in the homology class of sphere, and more even have to be homeomorphic to sphere. Its projection have to be homotopy equivalent. But what is not known? Okay, of course, it's not known that it's Hamiltonian isotopic, but it's not even known that it's diffeomorphic. So the first question is kind of like which we don't know. Is it true that so if, for instance, exotic sphere can be embedded Lagrangian there as a Lagrangian submanifold cotangent bound of usual sphere, or kind of like even slightly weaker question, take a cotangent bundle of exotic sphere, a cotangent bundle of real sphere, are they symplectomorphic or not? So there is a theorem of Bouzaïd which says yes, they are not symplectomorphic, provided, say, one, for instance, standard, another does not bound parallelizable manifold. So this but it's very restricted class of homotopy sphere. For most of them, like for instance for 7-dimensional sphere, for any of the 28, all of them bound parallelizable manifold, but we don't know if they are the same or not. And so, but now it kind of like suppose you just think about this first. So take cotangent bundle of usual sphere, and this Weinstein manifold you can think it's follow way. You take a cotangent bound disk and attach this disk kind of along this one. And exotic look exactly the same, but when you attach disk, you parameterize it differently. And so therefore, we have a two Legendrian embedding of sphere, of standard and the same differently parameterized. And you, for instance, ask, are they Legendrian isotopic? So is this Legendrian unknot and the same unknot parameterized by exotic parameterization, are they isotopic as Legendrian? So, and even let's ask, is it possible to make this isotopy such that it projects to regular homotopy, right? So if you just said projection regular homotopy, then answer will of course always yes. But now this very special regular homotopy that Warnold called regular homotopy without dangerous tangencies. You're not allowed tangency where co-orientation is the same. And this is a kind of like, you just ask, are this reparameterized sphere are homotopic? Is that? And this kind of equivalent to looking at singularity of this type.